Hello and welcome. Year 12 stuff for today. Trigonometric equations by general solutions. This is one of the topics one of the topics that are most commonly asked. What is going on? Because not many teachers and many books actually cover it. So I'm going to show you how I solve trigonometric equations from the very beginning, basically from year 12. So I've got up there, where did I put it? I've got 6 questions, a sample of six questions, 2 sine, 2 cos and 2 tan. Very, very simple. And we're going to introduce some rules and we're going to go through them very, very quickly. So without wasting any time, let's start with the first equation. I'm actually going to write some rules here. So let me just separate this space so I don't invade it. So we're going to put the rules here. So these are our notes. And let's start with the first equation. Let's see what I'm actually doing. 4 times the sine of x is equal to 3. And we want to solve this trigonometric equation in the interval 0 to 360, the most common integral in degrees. Okay, where do I start? Well, first of all, let's divide the 4 from the front of the sine. So the sine of x is equal to 3/4. And after that, of course, I need the inverse sine. I call it, of course, the arc sine. You will never see me writing sine to the -1, cos to the -1, tan to the -1. I actually detest it. So the arc sine of 3/4 of your calculator, of course, in degrees is 3687 or thereabouts. You can actually write 36.9 for this because we will not need to divide and therefore we will not lose any accuracy. So what do I do? Let me write the first rule down before I actually solve it. I'm going to bullet point it. So the rule says the equation, the sine of theta is equal to some number a. It has 2 possibilities. I put it like a loop, like a curly bracket if you want there. So theta and theta, 2 families if you prefer, are equal to. The first is the principal values. What my calculator gives me is the arc, I missed C there, the arc sine of a plus or minus multiples of 360 degrees, plus or minus 360 n, where of course n is 0, 1, 2, 3 and so on, dot 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 forever. And the secondary family, the second one, is 180 degrees, if we're working in degrees of course, minus the arc sine of a again, plus or minus 360 n. Okay, just before we actually use it, the reason this happens, if you look at the graph of your sine, the sine graph, so we got there, I'm gonna put just up to 180 to see what's going on. If you look at the graph, it will go up to 1 at 90 degrees, then it'll come down and be crossing the axis again at 180. So when we're doing the inverse sine, let's say for this particular equation, so that's a straight line there. Oops, straight, not very. Okay, this is what my calculator will give me. It will give me this number here, where I'm putting a little arrow. Okay, so if I add 360 degrees, I'll be getting the same position on my wave graph, but on the way up to the mountain, if you want. Of course, there's solutions on the way back down from the mountain. Let's see what they are. If you look at where the principal value is, the secondary is 180 degrees. Take away the same distance backwards. It's not very symmetrical there as I drawn it, but I hope you get the idea. So this is why this thing works. So in our case, we're inverting x. That's the argument of the sine. So there's my bracket, or curly bracket if you want. X and x is equal and equal. The first one is of course 3687. Let's write 36.9 is better. 36.9 degrees plus or minus multiples of 360. I'll write it very formally. Dot dot dot. And the secondary value from 180, that's what that says in there. We're going to subtract, of course, 36.9, 143.1 with repeats of 360. And this is known as my general solution. It picks up all the solutions. The way we use it is very, very simple. We'll look at this number. First solution is 36.9. Is that in range? Of course it is. It is between 0 and 360. That's basically when I put n is equal to 0, so I'm adding nothing if you want. Now, do I get more solutions if I add 360? The answer is definitely not. I'm going to go over. If I subtract 360, I'm going to go negative. I'm not allowed. So this family gave me all the solutions. So I'll go to the second family. Is this bit here in range? Solution number 2. Yes, it is. It's definitely between 0 and 360, and I will get no more solutions by adding or subtracting multiples of 360, and therefore I am done. For this particular simple equation, these are the 2 solutions. Okay, so it's as simple as that. Let's look now how things become when the argument of the trig functions do change, because of course they're not going to be just x all the time. There'll be 2x's, 2x plus some angle or whatever. I'm going to rub off this graph as well. We don't actually need it because I'm going to put the cos rule in a second. The second equation is a cos equation. So it says 4 plus, let's switch pen because this black pen is died on me. 4 plus 2 lots of the cos of 2x is equal to 3. And the solution interval, let me just put it at least all in blue. 4 plus 2 lots of the cos of 2x is equal to 3. Solution interval again, 0 to 360. Okay, first of all, we need to tidy this algebraically. What that means is, of course, 2 times the cos of 2x is equal to -1. Subtract the 4 to the right. And then I'm going to divide by 2. Careful, this 2 here, not this one in here. Strictly speaking, that's the argument of the cos, and it should really be in brackets, although we don't write them because they're implied. So the cos of 2x is equal to -1/2. Once I'm at this stage, I need the inverse cos. The arc cos of -1/2 of my calculator in degrees is 120 degrees. So I need to know now how to set up my general solution here, like I've done for the sine. I'm going to go to the side. Apologies that I'm mixing colors here, black and blue. Probably on the video there, I was watching the video, it doesn't have much difference actually. I cannot actually tell the difference between blue and black on the video. So the cos of theta now is equal to a. There are 2 possibilities again, theta and theta. The principal value for this equation is, of course, what my calculator gives me, the arc cos of a, and I have repeats or adds, if you want, or subtracts of 360 degrees. Same formal notation for this. And how about the secondary? For the sine was 180 minus, for the cos is in fact 360 degrees minus the arc cos of a, and again it repeats every 360. I just want to say something of interest there. If you look at work of mine that dates back to perhaps the late 1990s, I think as late as that, this particular general solution, for the cos, I used to write compactly the whole thing as theta is equal to plus or minus the arc cos of a. It's exactly the same, and I'll explain why I don't use it anymore. So this line here is equivalent to both of those. The reason I don't use it anymore, there's nothing wrong with it, first of all, is purely, I'll use it maybe now at undergraduate level or if I'm doing things for myself, is purely because usually in exams, the solution interval is positive. It'll be 0 to 360, 0 to 180, and so on. And if you're using this, you're always getting a negative answer, which you have to always adjust and go into range. So this has an extra line if you're using that, usually for A-level exam, so I avoid it. But just in case you see it and you're just wondering where is it coming from. Okay, let's return to our question. Now we need to set up the general solution here, like we've done before. So what are we inverting? 2x. 2x and 2x equal and equal. according to my general solution there, the principal value is 120, what my calculator gave me here, with repeats of 360 degrees. 1, 2, 3, dot, dot, dot. What's the secondary one for a cos? The secondary one for a cos, I'm not going to write it here. I'm going to write the little workings here. 360, take away 120. And this is where this 240 is coming from. Plus or minus 360n. Have I finished with this particular general solution? The answer is not quite. The reason is because I have 2x rather than x. So what I'm going to do on the next line, divide the whole equation by x. So x and x, equal and equal. Halving gives me 60, but now it repeats every 180. Halving the 240, 120. It repeats, of course, as the line above, 180. And I'm ready to pick up solutions now in the interval that is specified. Solution number 1. I'm starting with the first family. Is 60 okay? Of course it is. We'll write it down. Can I add another 180 to that and still be in range? Quite clearly I can. 60 plus 180 is 240. And that's the second solution from this family. Can I add another 180? 240 plus 180 clearly will go over 360. So I stop there. Clearly if I subtract, I go negative, not good. So I go to the second family now, solution number 3. So I'm looking at this now. The 120 is okay without adding or subtracting anything. And I will get one more solution, x4, by adding 180 to the 120, so 300. No more by adding, and definitely no more solutions by subtracting 180 from the 120. And this is, of course, now the 4 solutions that balance this particular equation in this particular interval. So that was question number 2. And of course, we try to mix it. So we go into a tan next. And tan is a lot easier than the sine and the cos, as you will see. So the equation that we got is 2 tan of x plus 40 is equal to 1. Solution interval for this, again, 0 to 360 in degrees. Okay, first of all, I want to say something, particularly to for year 12s or for people that just are new to trigonometry. This is not a bracket that you multiply out, okay? So be very, very careful, because many students, the first time they see things like that, they treat it as a bracket. For example, 3 times x plus 40, quite clearly, is 3x plus 120, no problem there. However, this is not a bracket. Well, it is a bracket, but it's not like a bracket like this one. This bracket signifies the argument of your trigonometric function. That means that's the belly, if you want, of the tan. That's what's inside the tan. Okay, it does not obey rules of brackets or anything like that. So we cannot take this 40 out of there or do anything else. However, these 2 at the front, we can divide it quite clearly. So that's the first thing I'm going to do. So the tan of means argument of x plus 40 is 1/2. Next thing, once I get to this particular line, is I need the inverse tan, the arctan over half in degrees, 26.6 to 1 dp. And now I need to set my general solution. So let's write the third and final rule. This is my tan. The tan of theta is again some number, let's say a. So what are the rules now for the tan? Okay, theta and theta, like the other 2. As you can see, the first family is always the arctrig, is the arcsine, the arccos, the arctan. So I'm expecting, of course, the arctan, what my calculator will give me. That's the arctan of A, but the tan repeats every 180 degrees. So that's a little bit different. 0, 1, 2, 3. What about the second one? Well, the second one doesn't exist. Okay, so why did I write a bracket like this for this one? I just feel sorry for the tan. He might be upset, and he might say, well, how about the other two that have two families, and I don't want to be a second-class citizen, so I always give him a bracket, although I don't use it. That may be bizarre, sometimes I do crazy stuff. So I do mean this. I always write this in my solutions if you see them. Okay, so at the moment, is it a theta? So I'm writing stupid things for a second. What are we inverting in this particular question? What's the argument of the tan once we are ready to go, basically? We're inverting x plus 40. So that's not theta. I got carried away from writing the rule down there. So we're inverting x plus 40. That's the bit inside the tan. And I have now, that's equal to the number my calculator gave me, in degrees, of course. And it repeats every 180. N is 0, 1, 2, 3, and so on. What's my next line? Well, my next line is going to take care of this 40. Let's put the 40 degree there because it's better. How do we subtract it? Okay, we will take that. Do we subtract from that, or do we also subtract from the 180? Careful again, because people often are getting sloppy and they don't write the N. So let's look at this with smaller numbers, and let's go back a few years in our maths. So suppose we had x plus 3 is equal to 5 plus, I don't know, 7n. And we want to make x the subject. I hope that your x is 2 plus 7n, and you don't subtract this 3 from the 7n. These are lots of 180. That's why I write n there. Okay, so we can only subtract it from that 26.6. So x is now equal to, we're going to go to the negatives, unfortunately. 13.46. Yeah, I think it's 13.4. I hope I'm not making stupid mistakes. I'm just too lazy to grab a calculator at the moment. So if I am, please feel free to laugh. 180n. So now this is ready to give us solutions. Solution interval 0 to 360. So the first question to ask, is this number, without adding anything, in range? Is not in range, unfortunately. It's a good answer. It will balance this equation, but whoever set the question does not want negative numbers, only wants from 0 to 360. So in order to get our first solution, we need to take the minus 13.4 and add 180. This will give us 166.6, I think. 167, 170, 180. I think it's good. And then we can get another one if we take this now and add another 180 on top of that. That will give us 346.6 degrees. And these are the two answers that balance the tan equation that we got up there in the interval 0 to 360. I hope you all make sense so far. These rules look quite daunting, but I promise you, most students, after they do maybe 10 questions, they begin to memorize, and after that, they're just as easy as anything. These rules, by the way, a little bit more formally than how I've written them up there. They used to be practically standard material in all the syllabi in the United Kingdom until 2001. And after that, they were taken out of the syllabus, and I think it's only AQA, if my memory serves me well, that kept this kind of work for the FP1 module until 2017. Maybe another board, which I can't think at the moment, also kept it, but it is not being taught anymore, unfortunately, and I think it's a real shame. Okay, we're going to go to question number 4 now. We're going back into sine. So we've done sine cos tan. We're going to do another sine cos tan. I'm going to do one in radians as well for year 13s. So the next question is 4. The sine of 3x, argument is 3x, perhaps I should put in a bracket, is equal to the square root of 6 plus the square root of 2. And the solution interval is 0 to 360, no, to 180 for this one. Okay. What about these surds? Are they a problem? I don't think so. These surds are there purely to make the numbers work really well. So this 4, which is in front of the sign, 4 lots of this, I'm going to divide it. So the sine of 3x is the square root of 6 plus the square root of 2 over 4. And then we need to do the inverse sine, if you want, the arc sine of this mess. These are just standard numbers. The sine of 15 is the same as the cos of 75. And I'm going to write the values in a second. And the same way, the cos of 15 is, of course, the same as the sine of 75. And they're pretty much identical. The one that we got up there is the sine 75 or cos 15. That's root 6 plus root 2, the whole thing over 4. And the other one is exactly the same, but with a minus. So the reason these numbers are there is just purely to make our life easy. So the arc sine of ... all of this, if you want, okay, it's going to be 75 degrees off your calculator. That's just by the way, I'm not saying you should memorize this, not at all. I will just try to explain why this particular set of numbers, okay? This, of course, you use your calculator. Okay, so now we're ready to set up a general solution using this number. It's a sine. What are we inverting? 3x, of course. 3x and 3x equal and equal. We're looking now on our general solution for a sine. 3x, principal value is, of course, always what our calculator gives us, 75 degrees. Sine and cos repeat every 360, as you can see in there, plus or minus 360n. And the secondary one for a sine, 180 minus, so 180 minus will take me to 105 degrees, plus or minus 360n, where n is 0, 1, 2, 3, ... I hope this mic is okay because it's been making funny noises. So if you're hearing anything funny, it's not me, I promise you. I can't even hear anything. I will hear it obviously once I play the video afterwards. So I hope it's okay. Where are we? Next thing from this line here, we need x and x. X and x equal and equal. Divide the whole equation by 3. 25 degrees plus or minus. Now we'll be adding lots of 120. Dividing 105 by 3 is 35. And again, it repeats every 120. And we're ready to pick up solutions now. The interval for this one, remember, is only 0 to 180. It's been shortened clearly because this adds every 120. If we left it not to 360, we'll have way too many solutions to write. Not that it matters, but just to keep it a little bit more sensible. Okay, solution number 1. Look at the first family. Is 25 in range? Of course it is. 25 degrees. My handwriting is getting worse by the minute. Sorry about that. Equal. Okay, still on this family. Can I get more solutions? By adding 120. If I add 120, I will get 145 degrees. So that's good, still within 180. No more to add. And we cannot subtract because we're going to go negative. We go to the second family now. Solution number 3 is the number at the front, okay, and in range, definitely, 35. And solution number 4, we will get one more by adding just one lot of 120 to the 35, 155. I hope I'm not making mistakes because I'm very, very tired at the moment. And these are the 4 solutions for this equation and for this interval. I hope so far it all makes sense what I'm doing. I definitely have no intention. I never teach all this kind of but by the way, for those who are using graphs, like I just drew up there to solve the trigonometric equations, I have nothing against it. It's actually okay. What these rules are in fact graphs, but without drawing your graph. Definitely, I would not recommend, and I don't even know how to use what you call it, a cast diagram. I just hate it, really. It's just mad, really. It makes no sense, and it's just cumbersome and very, very painful. Okay, next question. we're back to a cos. This is question number 5. The cos of 4x plus 12 degrees is equal to, no number, is actually equal to the cos of 132 degrees. And the solution interval minus 90 to 90. Doesn't really matter. Let's put it doesn't matter. And that's Rx. Okay. What about this? Quite crazy. One way of looking at this particular equation, if you're unsure, and I had a student once that got the AQA used to give this quite a lot in their exams in the past, and he said the way I solved it was to find with my calculator the cos of 132, and then I've done, of course, whatever number that gives you, and then I've done inverse cos, and I use that number. Well, if you put on your calculator the cos of 132, it will give you some negative number. I don't know what it is, some decimal less than 1, of course, numerically that is. And then if you do inverse cos, you leave it as an answer on your calculator, you invert it, it will say to you 132 back. Okay, so that's okay. But in fact, we don't even need to do that. We have cos of this lump is equal to the cos of this lump. I'm going to go straight into the general solution. That's a little bit bizarre what I'm going to do, but it makes sense. 4x plus 12 and 4x plus 12 from the bracket on the left. Equal and equal. 132. But of course, I repeat every 360 degrees. Remember, we're a cos and we're looking at this particular rule there. What's the secondary one for a cos? 360, take away the number you put in there. 360, take away 132. God, that's a challenge without a calculator, but I'm still way too lazy to go and get one. 2 from 10, and then we've got 1, 4, 2, 2 to 8. I'll make it. I hope it's right. 2 to 8. That's of course your 360 if you want, minus your 132. Just make sure you know what I was just doing in there from this line here. Plus or minus 360 n, where n again is 0, 1, 2, 3, dot, dot, dot. What do I do next? First of all, we got a couple of things to do for this particular question. First of all, deal with this 12. Remember, this can only attach to just numbers on their own on the other side, so we can subtract it from 132 and we can subtract it from the 228. So 4x and 4x. We can do it, I guess, in one go with a calculator, but I will say to you, please take your time so you don't make any silly errors. So taking away 12 from 132, nice number, 120. This of course does not change. And 228 take away 12, 226, 216. Not so nice, but it's not too bad. And then of course we need to divide the whole set by 4. X and x equal and equal. Divide this equation by 4. It will give us 30 with repeats of 90 degrees. And if we divide 216 by 4, half it is 108, half it is 54. So it's 54 degrees plus or minus 90n. Okay, I'm ready to get solutions as before. So my solutions now are going to be looking at the first family. 30 is okay and in range. Remember, the interval now is minus 90 to 90, quite a small interval in degrees. So I cannot add 90, I'm going to go over, but I can definitely subtract 90. This will take me to minus 60, which is okay. There will be no more by subtracting a further 90. I'm going to the second family, x3. The 54 is okay without adding or subtracting anything. I cannot add, but I can subtract 90. That will be, is it 36? 36 it is, negative 36 of course. Okay, and I cannot take it more any more 90s because I'm going to go below negative 90. These are your 4 solutions for this particular equation. So that's the question number 5. And I got one more question. If you're in year 12, maybe in your school you won't be doing radians. Most schools in year 12, they will do trigonometric equations, but in degrees only, and they will leave radians, which is just a different unit really, for year 13. So if you're year 13, of course you would have seen radians. So I've got one question in radians just to get the idea. There's no new rules to learn. The only thing you have to be careful is, of course, when you're using this, when your calculator must be in radian mode. And of course the multiples of 360 are now 2 pi n, the multiples of 180 pi n. And when you're doing for a sine 180 minus the arc sine, of course that will be pi minus the arc sine, and this will be 2 pi minus the arc cos. The one I've got for us up here is a tan one, so let me just write it. Square root of 3 plus the tan of 3 over 2 x plus pi over 3. All of that is the argument of the tan, is equal to 2. And stupidly I've written the range in degrees. How stupid I am sometimes. Okay, I've written here not to 180. So of course we're going to write it in radians. So that's from 0 to pi. And I want the answers in terms of pi. So this particular one should give you decent answers, and we're gonna leave it in exact form. Okay, what do we do? This, of course, is not a bracket. It's the argument of the tan. Cannot be touched, cannot be messed around with until we're ready to invert. However, this root 3, we can actually subtract to the other side. So it's best to leave it exact. And the reason it's best to leave it exact is because this is a nice number. The arctan of 2 minus the square root of 3 is 15 degrees, and 15 degrees in radians is pi over 12. Of course, off your calculator, yeah? So this is now, I need to set a general solution. This is my principal value. Let's look at the tan equation. It's just very, very simple. Only one family, but of course I'm going to give him space for 2. Try to keep him happy. I'm inverting 3 over 2x plus pi over 3. That's this bit here. And of course, it's that quantity that my calculator gave me. And it repeats. In degrees, of course, it would have been plus or minus 180. But we're in radians for this one. So radians plus or minus pi n, where of course n is 0, 1, 2, 3, dot, 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 dot. We're going to do things in stages. So first of all, for this particular one, let's subtract the pi over 3 to the other side. So 3 over 2x is equal to, that again using your calculator, I'm going to work in degrees and just write the answer. So that's a 15 and that's a 60. So it's going to give me a negative 45, and a negative 45 in radians is minus pi over 4. So that's the pi over 12, take away pi over 3 on your calculator, plus or minus pi n. After that, we can actually use the calculator and divide everything by 3 over 2. I'm going to do it in 2 steps. So first of all, I'm going to double the equation. So 3x, I'm doubling this, so it's going to go minus pi over 2 plus or minus 2 pi n. And what do we go next? We divide by 3 quite clearly. X is equal to, divided by 3, that's a 90, divided by 3 will go 30, and 30 is minus pi over 6, plus or minus, and this will go 2 pi over n over 3, or if you want, 2/3 pi n. And the mic is on my feet. Hopefully I will not trip. Okay, so now I'm ready to pick up my solutions. My solution interval is 0 to 2 pi. So at the moment, of course, the leading number is not in range because it's negative. So we need to add 2/3 pi first of all. So that's solution number 1. So that's a minus 30 That's the minus pi over 6. And we need to add 2/3 pi, that's in degrees is 120. So it will take us to 90. So that means the first solution will be pi over 2. That's by adding 2/3 pi to that. And can we get another solution? We're going up to pi. We are at 120 as it is. Sorry, I'm working in degrees at the moment. Use your calculator, obviously, yourselves. If I add another 120 to that, so I'm at 90. And if I add another 120, that's your 2/3 of pi. It will take you to 210, which is above 180, which is above pi. So in fact, this particular question only has one solution, and that is pi over 2. And that's practically the end of this question. I hope this was educational. You can now understand better what I'm actually doing in my books and in my papers when I'm solving trigonometric equations. That's the only method I use, which is very, very useful. It cuts out any kind of graphs, any diagrams or whatever. It's fully algebraic, as you saw. It doesn't matter what you give me. You can give me the most disgusting thing. The algebra will take care of it. And please give it a go. If you're using graphs, it's actually graphs without doing a graph. The reason this rules works because of graph symmetries and nothing more. Okay, I hope you found that useful. Join me again, and who's laughing now? I certainly am right now.